Hi there, and welcome back to Math 107. I guess I shouldn't be saying welcome back. You've already watched one video, but for the last one, I didn't really need to write anything for you. I could sort of talk through what was showing up in the PowerPoint slides. Now, I kind of have to be able to write in real time, and I don't have the technology to have the board and the PowerPoint slides up at once. So ground rules, I'm going to take for granted that you have the PowerPoint presentation there with you, be it digitally or printed out, that won't matter. Additionally, there's going to be another handout that you should be able to find in our Moodle course that you should have available for this. I'll wave it at the camera momentarily, but I don't want you to have to keep pausing and jumping back to that spot in the video just to see what's going on. So we talked about inductive reasoning in most of the last video, where we talked about gathering data and then using that to draw conclusions. It has kind of a downside in that it doesn't really prove anything. You often use words like conjecture or hypothesis to describe inductive conclusions, whereas, so those aren't, those are fancy words for guesses, right? Deductive reasoning, on the other hand, gives us a more ironclad way to describe what's going on. We work from some sort of general base principles and then drill down to a specific conclusion. I wanted to revisit that example at the end of the last video dealing with the regifting Robin calculation. You may recall, hopefully, because you may be watching this video like moments after you just wrapped up the last one, that the regifting Robin process had us subtract a number's digits from itself, and through some process we couldn't quite, establish at that stage, it looked like we were always getting multiples of 9 back, and that let the regifting Robin app know exactly what sort of thing it should end up tossing back at us. So we did inductive data gathering and inductive reasoning to work that out. Now let's do some deductive reasoning to determine exactly why it's happening. The base principles in this case are algebra. It's okay. This is about as much algebra as we're going to see in the entire semester. Don't get too scared that there's going to be a lot of it in case that's not your strongest suit mathematically. But that's the best way to handle what we're talking about as far as this particular calculation is concerned. So I'm going to take my 2-digit number, whatever it is, and I'm going to represent it with some variables. So I want to call the ones digit of my number D for digit. I would use O, but that looks like a 0. The tens digit I'm going to call T. So I can algebraically interpret my 2-digit number then like so. 10 times the tens digit plus that ones digit D. So 10T plus D. We can't just write TD because that's not really mathematically what we're doing. We need to describe it using math operations. So that's what our number looks like in terms of these variables. Then subtracting the digits tells me, well, I subtract the tens digit, the T. I subtract the ones digit, D. Hopefully you remember from algebra, plus D minus D. They vanish in a puff of logic, and that leaves me with 10T minus T. And you can check from working that out really quickly. You got 10 of something, and you have to take away one of them, you're left with 9 of the something. So, and if you go back and look at our examples from last time, every time we ended up with 9 times our tens digit. So that's how this process is working out, and it does in fact confirm deductively that regifting Robin's process, if you do it right, is always going to drop you on a multiple of 9. That's why they all have the happy face modes. So that's that. Parlor games like this were, from what I understand, all the rage in like Victorian England, where you would walk through this weird set of arithmetic steps and always end up on, a particular number, or you would always get your original number back or something like that. This is as intense as we're going to look at it this semester, because the rest of our deductive reasoning examples are going to be following kind of a different tack. So what we're going to be looking at are logical arguments. So it feels possibly not like something you'd expect to see in a math class, but it's a good example of logic in action. Argument analysis is the kind of thing that, it's good to be able to parse the logic of someone's argument, and as time goes on, it only feels more and more relevant the more and more arguments I end up seeing. So the types of arguments we're going to be looking at are what we call syllogisms for this course. We'll eventually maybe get a little more sophisticated by the end of the chapter, but for now, we want to take a look at these things we call syllogisms. It's a pretty old thing. Aristotle looked at them, so to give you a sense of time scale here. So a syllogism is basically structured in 3 steps. You're given one premise, called the major premise. I usually just say premise. Second premise or minor premise, and then a conclusion. Usually it begins with therefore, or thus, or something conclusive sounding. The idea is something like, all cows have 4 legs. Bessie is a cow, therefore Bessie has 4 legs, that kind of thing. So hopefully that gives you an idea of the setup of these kinds of things. And what we're going to be looking at is trying to figure out how we can determine whether a given syllogism argument is what we call valid or invalid. So you might have heard in the last video I talked about that claim about old presidents being invalid. That's kind of why. So I'm taking a look at our first example here. It mentions mathematicians, so hopefully that feels mathematical. So we have one premise that says all mathematicians are logical. The second premise says one specific mathematician, Sir Isaac Newton. Yes, he was a mathematician, not a physicist. Don't come at me. And then the conclusion says, therefore, Sir Isaac Newton is logical, or was logical because he's dead. Anyway, so in terms of trying to figure out how we can determine whether or not this is valid or invalid, we're actually going to revisit one of our tools from chapter 1. We actually can look at a lot of these arguments using Venn diagrams. So if you take a look, the structure of a lot of these syllogism arguments end up saying all A are B, or some A are B. So to that end, I have posted a file with some sample Venn diagrams for particular argument structures. All A or B, some A or B, no A or B. Again, this is in Moodle. Don't feel obligated to try to print a screenshot of this or something. Okay, so now we're going to take those formats and translate our argument into a Venn diagram and see if it holds up. So premise 1 says all mathematicians are logical. That looks like that first bullet point. I'm pointing at a thing you can't see off camera. I should probably stop that. That says all A or B. So I need a couple of circles, one inside another, and I usually label them like this. It says all A, that's mathematicians for this particular sentence. So I've got my mathematicians right there. All mathematicians are logical. B is logical. That's the guy on the outside of that format. Premise 1 is now sketched out visually. This Venn diagram details exactly what we've got going on. The second premise says we have one specific person who is a mathematician, Sir Isaac Newton. We can actually represent a single instance of an individual by representing a single point on our Venn diagram. You could technically do another circle, but it's kind of overkill. So the Sir Isaac Newton dot needs to go into the mathematician circle because that's what the premise says. So I need a dot in here. I'll abbreviate Isaac Newton IN. That's not the best N I've ever written, but we're going to go with it in the interest of time. Technically, I could have drawn it over here, or over here, over here. It just has to be inside that math circle. And now we take a look at the conclusion because we know we've drawn the diagram, so both premises hold up. Does the Isaac Newton dot have to live inside the logical circle? Is there a way I could redraw this so Isaac Newton stays inside here but gets outside the logic circle? No, I can't. No matter where I put it, he's still going to be inside that bigger circle because he's got to stay in the little one. So we would say, as a result, this argument is what we call valid. We don't refer to arguments as being true or false. It's basically whether their logical structure holds up or not. That's why we choose to say valid or invalid. So that's one example. I want to take a look at another one real quick. I will be real upfront about this. This is an example from the textbook, but I think it illustrates a point that I want to make really, really well. So, looking at that next example, it says, all pro wrestlers are actors. The Rock is an actor, therefore The Rock is a pro wrestler. So if we follow through the logical structure like we did with Mr. Newton before, all wrestlers are actors. That's that same setup. I need those same two circles. Which one goes on the inside? That's right, wrestlers go on the inside because that's in the place of the A in our format. So I'm just going to abbreviate rest. So, sorry. Then it says all wrestlers are actors. So, the wrestler circle is living inside the actor circle. Premise 1, done. Premise 2, The Rock is an actor. So that means I need to put a dot, just like I did for Isaac Newton earlier, into my diagram. Where does it need to go? Does it need to be in here? It says it needs to be inside the actor circle. So I could technically put it right there, but it's not required. I'm going to draw it over here, and I'm just going to say R for Rock. So hopefully he doesn't come after me because he doesn't like that I'm not calling him Dwayne. Anyway, so we're satisfying both of our premises. The wrestler circle lives inside the actor circle. The dot for The Rock is also inside the actor circle. The conclusion says, The Rock is a wrestler. I didn't have to draw it in there, so no. This argument does not hold up. This is what we would call an invalid argument. I like pointing out this particular example because if you look at the individual sentences, each one you can make a pretty good case that they're true. Okay, I'm not going to get into pro wrestling debates at this point, but we're going to take for granted that all pro wrestlers in some measure are in fact actors. The Rock is credited as an actor in a lot of movies at this point. Seriously, the guy's everywhere. So that checks out. Whether or not you call him a wrestler right now, I don't know the status of his contract with the WWE or whatever. But anyway, most of us probably wouldn't argue with those three individual sentences being true on their own. It turns out, though, when we put them together in this particular logical format, we end up with something that's not what you might call an analog of true. So I do like using the example just to suss out that the logical structure of the argument is actually independent in some sense of whether or not the individual component statements that go into it are true or false. There's a similar argument, if I recall, in the textbook where they use false sentences but then construct a valid argument out of them. So that's a little tricky. I want to take a look at a couple more examples of this, so I'm going to make another video where we can see what happens if our premises aren't just quite this all A or B, here's a point, where does the point end up falling? So stay tuned.